Welcome to the Explainer. Have you ever wondered why traits like blue eyes or red hair, which are recessive, haven't just vanished? I mean, it seems like the stronger, dominant traits should have completely taken over by now. Well, the answer is not what you'd think, and today we're going to dig into that exact genetic puzzle. So let's start with a question you've probably kicked around since high school biology. There's this common idea that dominant genes are kind of like bullies, eventually shoving all the recessive genes out of the picture. But if that were actually true, we'd all pretty much look the same by now, right? The real story is so much more interesting. Here's the twist. The answer isn't really about strength. It's about scale. To get to the bottom of this, we need to zoom way, way out. We have to stop thinking about a single family, one specific couple having kids, and start thinking about the genetics of entire populations. See, what most of us learn in school is Mendelian genetics. And it's awesome for predicting what might happen in one family. But population genetics, that's a whole different ballgame. It's not about one neat little family tree. It's about studying the whole messy, tangled, interconnected forest of an entire community's genes. And in population genetics, the real unit of action isn't the individual. It's something called the gene pool. Just imagine for a second, taking every single gene from every person in a town and tossing them all into one giant bucket. That bucket, all the alleles, all the different versions of genes, that's the gene pool. It's all the genetic material the next generation has to work with. So in the early 1900s, two researchers, a mathematician named G.H. Hardy and a physician, Wilhelm Weinberg, they independently came up with this absolutely brilliant, kind of backward idea. Instead of just trying to measure evolution, they asked, what would a population look like if it wasn't evolving at all?
And what they came up with was a mathematical model for a perfectly stable, totally unchanging population. This state is called the Hardy-Weinberg equilibrium. You can think of it as the ultimate null hypothesis for evolution. If a population's genes match the model's predictions, well, it's not evolving. If the numbers are different, then you know something interesting is going on.
And for a population to hit this perfect equilibrium, the rules are super strict. No new gene mutations, everybody has to mate completely randomly, there's no natural selection, the population has to be huge, and nobody can move in or out. And you're probably thinking, wait, no population on Earth is actually like that. And you're totally right. It's a theoretical baseline, kind of like a physicist imagining a frictionless surface to understand motion. It's a simplification that reveals a powerful truth.
And the math behind this is surprisingly elegant. It really just boils down to two simple equations. The first one tracks the alleles themselves. We just say the frequency of the dominant allele, which we call P, plus the frequency of the recessive one, Q, has to equal 100%. The second equation predicts how those alleles will actually show up in people across the population.
And this is where it gets really cool, because each piece of that equation maps directly to a group of people. P squared, that's the percentage of the population that has two dominant alleles. Q squared, that's the group with two recessive alleles. They're the ones who actually show the recessive trait. And that middle part, 2pq, that's the frequency of the heterozygotes, the carriers who have one of each allele but don't show the recessive trait.
And right there, that is the answer to our big question from the beginning. As long as a population is in this theoretical equilibrium, the frequencies of P and Q don't change. The simple math of random shuffling from one generation to the next keeps the gene pool perfectly balanced. Dominant traits don't take over because the system itself protects the recessive alleles. But what happens when that balance gets broken? You see, the real power of the Hardy-Weinberg principle isn't in finding stable populations. It's what the model tells us when it's wrong. When the gene frequencies in a real population do change from one generation to the next, that's like a giant flashing sign telling us that evolution is happening.
And it turns out there are 5 major forces that can break that equilibrium and drive evolution. Each one messes with one of those ideal conditions we talked about, whether it's creating new genes, making mating picky, or having the environment favor one trait over another. When any of these are active, the gene pool starts to shift.
Let's look at a classic textbook example of this: the peppered moth in 19th century England. Now picture this. Originally, almost all of these moths were a light speckled color. It was fantastic camouflage against the lichen that grew on trees. The dark-colored version existed, but it was super rare. This timeline perfectly illustrates natural selection in real time.
The Industrial Revolution kicks in, and soot from factories starts coating all the trees, killing the light-colored lichen and turning the bark black. All of a sudden, those light moths stuck out like a sore thumb for birds. But the rare, dark moths, they were now perfectly camouflaged. Their survival rate shot up, their allele frequency skyrocketed, and the population's gene pool evolved right before everyone's eyes.
So if no real population is ever in perfect equilibrium, you might be sitting there thinking, okay, then what's the point? Why are we even talking about this imaginary perfect world that doesn't exist?
Well, the point is that this imaginary world gives us a perfect baseline to measure the real world against. And even more critically, it gives us a tool to calculate things we can't easily see, like how many people in a population are silently carrying the gene for a recessive disease.
Let's take a real-world example. The genetic disorder cystic fibrosis. It's a recessive disease, so you only have it if you inherit 2 copies of that recessive allele. Now, we can go out and count how many people have the disease. In some populations, that number is about 1 in every 3,000 newborns. That observable number, that's our Q squared.
And now we can do a little genetic detective work. We can use the Hardy-Weinberg formula and just work backward. We know Q squared, so we take the square root to find Q, the frequency of the allele itself. Since P and Q have to add up to 1, we can easily find P. And once we have both P and Q, we can plug them into that 2PQ term to calculate the frequency of the hidden carriers.
And when you run the numbers, you get a frequency of about 0.035. What does that mean in the real world? It means that roughly 1 in every 28 people in that population is a carrier for cystic fibrosis, without showing any symptoms at all. That is an absolutely critical piece of information for genetic counseling and public health. And we found it using a purely theoretical model.
The model also gives us this really elegant explanation for why recessive traits linked to the X chromosome, like red-green colorblindness, are so much more common in men. See, a female needs 2 X chromosomes with the recessive allele, so her probability is Q squared. But a male only has 1 X chromosome. He just needs that 1 to be recessive, so his probability is simply Q. If Q is, say, 10%, his chance of being colorblind is 10%, while a female's is just 1%. So at the end of the day, this simple, elegant model of a non-evolving population is so much more than an abstract idea. It's a powerful lens. It gives us the vital baseline we need to measure and understand the real evolutionary forces that are constantly shaping all life on this planet, including us.
And that leaves us with one final, pretty provocative thought. We know the forces that can change a gene pool. So when you think about our world today with modern medicine, global migration, and a changing environment, you have to wonder, where is the human gene pool headed next? Thanks for watching The Explainer.